Good. Okay, so the moral of the end of last lecture is here, is that it's a crucial point. Once you discretize and do the path integral for a theory defined that evolves in a Newtonian time or in a background time or in a physical time, then the continuous limit is obtained by taking the number of steps to infinity and bringing a constant to its critical value. Okay? Which is a general way of thinking about that. But when you do the same for a theory which is written in a parameter time, there is no critical value to take. And the limit is just the limit in which you get the number of you take the number of variables to go to infinity. So the difference between this formula, which is n going to infinity, and this formula, which is n going to infinity, and omega epsilon going to 0. And this is the core of the distinction between quantum gravity and quantum field theories, between spin foam and lattice QCD. Lattice QCD, in front of the action, you have the lattice spacing that you have to take, or the Yang-Mills coupling constant that you have to take to 0, to the critical value. Here not. So let me. This is a super simple example, of course. This is a harmonic oscillator discretized with independent Q and T variables. Let's do that for general relativity. Without going to the quantum theory, just to the full quantum theory. And there's a very clean way of viewing this, which is what Regge did in the 60s or 70s, very early, when Tullio Regge did the first clean discretization of general relativity, which is called Regge calculus. I'm not going into all the details, but is important because it shows how you discretize a theory without a parameter, and what is the truncation in. And it's important because to do the classical limit of the loop quantum gravity transition amplitudes, that's the intermediate step. So it gives exactly the clean intermediate step connection between AQG and classical general relativity. So what Regge did is his idea was to take a Riemannian manifold and truncate it, discretize it, and in terms of the discretization, write the Einstein-Hilbert action, or write the Einstein equations in terms of the discretized variables. And the way he did it is is the following. The simple way is to think in 2D first. In 2D, you start with you discretize your two-dimensional space with triangles, and you assume that all the triangles are flat. And given a curved surface, you can take small enough triangles so they are flat and they reproduce the. And the Regge idea is to use as variable the length. This is of this segment. We shouldn't call them links because they do not correspond at all to the links of the discretization for a reason. For the link of the LQG, for a reason I'll say in a moment. Where is curvature? Well, it's very easy because if you have the three links, you can compute this angle. If you have these three links, you can compute this angle. You can compute this angle, this angle, this angle, this angle. And clearly, if curvature here is the fact that the sum of these angles do not sum to pi, they can sum to less or more than 2 pi, and that's how you get curvature. So this angle here, let me call it theta, you can write explicitly in the function of as a function of the three L's around it. This is just elementary geometry, right? It's Euclidean geometry. And with that, you can compute delta, which is 2 pi minus the sum around of all the theta, all the angles, and this is a discretized version of the curvature. That's how Regge discretized the curvature. This is one of these for each point. Now, when you go to 3 dimension, you have tetrahedra. You do exactly the same game, and now you still use as variable the length. Okay, if you have the 6th length, you have the geometry of this thing. So from the 6th length, you can compute these angles here, the dihedral angles. This angle here. And when you have a number of tetrahedra around this bone here, you have the same formula. So you have the angles, a function of L, and you have a curvature, but now the curvature sits on one of these things here. Okay? So in 2 dimensions, the curvature sits on this, these things here. In 3 dimensions. In 4 dimension, you have photosynthesis. And now, if you have a 4 simplex, it's more complicated to view. It's bounded by 5 tetrahedra, and between 2 tetrahedra there is a face. And now, of course, in 4 dimension, around the face there aren't just 2 tetrahedra, but you have you can make a link. You can go around the face with tetrahedra. If you think that you have coordinate x, y, z, t, 4 coordinates, 2 determine the face. The other 2 you can go around it. So the triangle is a point with respect to the other 2 coordinates. You can go around it. So you have it's the same thing. Around the 4 simplex, you have 2 tetrahedra. These 2 tetrahedra have 2 normals around in the flat geometry of the 4 simplex. This gives an angle associated to the face between the 2 tetrahedra, right? When you go all around this face with all possible 4 simplexes, with all the tetrahedra around, you have all these angles, and this is the same formulas. Okay. And now the angles are functions of 10 segments which are around a 4 simplex. There are some elementary geometry formulas, and the curvature sits on the triangles. Okay, and then so this is what Regge did very simply. So and then he also proved something quite remarkable, that if you take the following expression, which is the sum over all the triangles in this 4-dimensional triangulation, and you for each triangle you take the area of the triangle, which of course you know if you have all, it's a function of all the length of the links. So this Regge action here is a function of all the length of all this the segments here, and you multiply it by the angle the deficit angle, this delta, associated to this triangle. Okay, you go around. You get an expression which, up to details, I'm just giving you the sketch of the story. I'm not going. There's some details I'm skipping. This is a number. It's a number that depends only on the L, So if all this L approximated some geometry, G mu nu of X, this is like a number computed out of the geometry. If you think for a while, what could it be? It's a number that depend on the G, depend on the curvature, sort of measure how much curvature there is. It's local because it's a sum of, so it has to be some integral on the manifold of something local, Lagrangian, which depend on the curvature. There are many things that it could be. So in the limit, the only thing that it could be is the Einstein-Hilbert action of the metric approximated by these links. And so Regge wrote this, and this was actually proved quite rigorously by putting the dots on what I've said. So there are mathematical there's a mathematical result that says that this expression here, if this discrete geometry approximates the continuous geometry in a proper sense, the difference between this and this is small in the approximation. This is just a sketch, right? I'm not giving you all the explicit formulas.
You say limit.
Huh?
You say limit on the number.
Let me be precise. So given a manifold with a four-dimensional metric, okay, and given an epsilon at your choice, you can always find a triangulation of it. Okay, so you draw a triangulation, you measure the length of all the things. Out of the length, you compute this quantity. This quantity is epsilon close to this. You can always find a triangulation such that this quantity is epsilon close to this. Of course, the triangulation has to be very refined if your epsilon is small. So in physical parlance, in the limit in which you refine the triangulation to infinity, to arbitrary fine triangulation, this converges to this. Okay? And this triangulation goes to infinity in this sense.
Refining the triangulation means
making the L smalls.
an infinite number of triangles.
Yes, making an infinite number of triangles. Exactly. Of course, what you prove has nothing to do with infinite. What you prove is that for every epsilon, you can find a finite number of triangles, but many enough for making this minus this less than epsilon. Okay? Which means that you can think, and that's of course how people have been thinking for a long time, even if it doesn't work because of hundreds of reasons. You can think of defining quantum gravity by taking a triangulation, integrating over all the metrics, namely integrating over all these L variables, okay, e to the I over h bar, this Regge action, function of the L, which is this one. Right? So you have all these variables, and this is defined for a fixed triangulation. So you can take the limit for a triangulation going to infinity, or if you want the number of tetrahedra going to infinity, and you can think of defining the theory this way. And now you see very clearly that there is no parameter here. There is no parameter to scale here. Why? For the same reason as the example described. The length of these things doesn't have to be taken to zero because it is integrated over. These are the variables being considered, the quantum variable being considered. So we're not fixing a size of the triangulation, we are fixing just a number of triangles and integrating over all possible sizes, which what you were saying before. So it's not a truncation in a scale. It's a truncation in the number of degrees of freedom which we're considering. So we have a manifold. We say I approximated geometry with a fixed number of degrees of freedom, and I have this expression. I can approximate with more degrees of freedom. I have this expression. There's a truncation in number of degrees of freedom. So it's neither a cutoff, neither an ultraviolet cutoff, nor an infrared cutoff, nor there's no size here. It's just number of degrees of freedom. And so this is Regge calculus. When we do go to loop quantum gravity, it's the same story. And the two complex and the graph on the boundary that we use is a truncation in number of degrees of freedom. It's neither a truncation for ultraviolet or for infrared, because this length can be larger or smaller, and the graph for loop quantum gravity, the J can be arbitrarily large or arbitrarily small. The reason the J has a minimum is just because it's quantized. So you cannot go lower. Yes?
Question. Could you comment on why these approaches failed? What are the problems with these approaches? So just quantizing the length rather than...
One of these, if you try to start to do things more precisely, is that these L variables are not independent because they are triangular inequalities. So already you're integrating on things whose domain of variation has an horrendously complicated shape because of all the inequalities. That's one of the difficulties that that you have. People have worked on that. There's a literature on trying to do quantum Regge calculus. In fact, good people worked on that, explored. It has never got much far. More than writing that and trying to, little has come out of that. I think that this triangular inequality is really the difficulty here. Once you rewrite this in terms of group variables, you free completely yourself from the triangular inequalities. You're in compact spaces. Everything just runs and goes. So if you want, loop quantum gravity is a way of doing this a little bit better. And in fact, in 3 dimensions, Regge himself with Ponzano wrote a version of that landed on what is called Ponzano-Regge model, which is very much loop quantum gravity in 3 dimensions. In fact, you go precisely to spin and intertwiners, and there's a chapter in the book about that. So loop quantum gravity, if you want, it's a way of doing this properly and cleanly. Good. Now, there's something more I want to say about Regge, because it's going to play a role, which is there is another way of this can be written by rearranging the terms. So this angle here is a sum, apart from the 2 pi, has a sum of the one term per each simplex around. So this can be written as a sum of term per each simplex, and the area can be associated with the different simplices. So the Regge action can also be written as a sum of the simplices of the sum on the triangles in the simplices of the area of the triangle times this angle theta, which is a function of the L, times this angle theta, which is a function of the L, this is the theta that depend on the simplices and on the triangle. Okay, this there. This is interesting because you see, e to the ISR is therefore the product on the simplices of this, the sum over the triangles of the simplex area angle. And remember that, so this is the action I over h bar. So this thing is the action for a single simplex, right? And remember that in the spin network amplitude that I wrote, the total amplitude is a product of action for amplitude for a single simplex. So the question is the quantity I wrote yesterday and this morning, which is a function of spins and intertwiner on the boundary of the for simplex, is it related to this one in some manner? Right. There's some step to fill out. What does it mean to be related? But if it is related to this one, this is the Regge action for a single simplex. When you put them together, you get the full Regge action, and you have this theorem that tells you that in some continuous limit, in the limit on which this thing small gives to GR, right? So we have reduced a way of analyzing this spin from amplitude that I have to a question about whether this vertex amplitude is related to this thing here or not. Okay? And that's the last thing I want to discuss. Now, to do that, there is a obstacle to overcome and a technique to developed, which to a good extent is we know it thanks to Simone, who just walked out of the room 1 second ago, and it's the following. So let me tell you what the problem is, what the solution is. There's a large literature on that, and slowly, probably not today, I'm going to tell you the details of the calculation. The problem is that let's go back to the spin networks. Gamma JL Vn. Okay. These do give geometrical information about the individual tetrahedra in terms of the area and one quantity, which can be the volume or the quantity which is diagonalized in intertwiner space. Okay? But these states do not have a direct geometrical interpretations for the following reason. Just think back to a wave particle, psi of x. These states, of course, are states that diagonalize position. These states are states that diagonalize momentum, but this momentum is completely spread. This position is completely spread. Now, do we have states in which we can represent a particle with a given position x and a given momentum p0, such that the spread is minimal? Yes, or is small? Yes, these are the wave packets, right? Kind of wave packet center in x with a delta x, which moves with a momentum p0, which is a certain spread, and we know how to describe these things here. These are semi-classical state, wave packets, coherent state. If I fix if I look at the states here, the geometry of a single tetrahedron, as we discussed various times, is given by 6 numbers. I have only 5 numbers, so it means that some quantity is completely spread. So can I write coherent states for the tetrahedron? Can I write a linear combination of these, which gives me a given shape of a tetrahedron, regular or non-regular, which minimizes the necessary spread in the various quantities? That's the first question. And the answer is that this can be done, and with a nice technique, which once you see it, it's very pretty, it's very simple, but before it took quite a while to figure it out. And it's largely due to Levin and Simone and Simone Speziale. So let me describe this technique. The idea is the following: we want, let's be more precise. We want a state for the tetrahedron where, let's say, the 4 areas are sharp. Areas are sharp. Okay. But the intertwiner is it describes as best as possible a given geometry of the tetrahedron, right? The intertwiner is in an element of the invariant part of Hj1 tensor Hj4. Okay? And the idea to do so is think later about the invariant part and write coherent states here. Write coherent state in the representation themselves. Because remember that the operator else, the L operator that we have, don't live here, live in these individual ones, and have a nice geometrical interpretation of the normals of this. So if you can make the operator L as semi-classical as possible, L are 3 operators, so I cannot diagonalize all 3 of them, but I can minimize the spread of all 3 of them. Here, 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 and here, I can describe a geometry in which the n, the 4 normal to the surface are semi-classical, are given, are minimally spread. And then I can take the invariant part of the state that I have. But take the invariant part of the state that I have means integrating over the rotations. So it means considering these 4 directions up to common rotations. Let's do it explicitly, and you see how this works. Let's take one of these things, Hj. We know a basis of state there, of course, it's Jm. And let's look at this Jm state. For generic M, the spread in, we have Lx, L1, L2, L3 acting on here. These are all eigenstate of Lz, L3, right? By definition, this is the quantum number of that. But they have L1, L2 pretty much spread. Not all of them. Think in terms of spherical harmonics, right? The spherical harmonics, for generic M, you have sort of spherical harmonic like that. But if you take the minimal M or the maximal M, the spherical harmonic it's here. So let's take the maximum of them, okay, Jj. So when M equals J, and this is a spherical harmonic that sits, so this is Z, this is X, this is Y, that sits on the top of the sphere. And in fact, Lz is sharp, Lx, Ly are minimally spread. And in fact, one can compute it explicitly, the spread, and it minimizes the spread. So we have at least one case in which we know a state where this is minimally spread, this is minimally spread, this points, this is as a fixed value, so we can interpret this as a semi-classical state. Well, Lz point in the z direction is good. So this represents a tetrahedron where this goes up in the z direction. Okay. Well, but we don't want to be attached to the z direction. We want to be able to turn it. Well, let's turn it. We know how to turn it because this is a representation of SU2. Rotation act on it. So given any unit vectors n, I can always choose a rotation matrix, which I call n also, following the clear Simone notation, that turns the z direction into it. Okay, and of course I can do it in various ways. Let's say that this I fix one, and then I can take my jj and rotate it with the j matrix, so with the action of rotated by this n, and this gives me j in the direction n. So I take this, I rotate it, I move this here, and this is my n vector, and there is a group element n that rotates in that direction. I use the same notation for the two. Okay? So this is defined by this thing here. So if you want Jm, Jm is a magnetic momentum number, and n is a vector, so it's going to be given by dj mj of the group element that rotate in the n direction. Okay? So now I have a state which corresponds to a vector pointing in a direction. I want 4 of them, so I just take 4 of them. I take J1 N1, tensor 4 of them, J4 N4. Okay, this depends on 4 vectors. So I have a tetrahedron. I have these 4 vectors. I have 4 areas, J1, J4, and this is a state which sits here. But now I want the invariant part. Well, I just rotate it, do a common rotation, and I integrate over all possible rotations. The result I get, of course, is invariant in the common action of SU2 because I'm rotating, and it does not depend anymore on the actual 4 directions, but it keeps the angle invariant. It depends on the 4 vectors up to a common rotation, namely depends on the geometry of this thing. So I now define, I take this, I integrate of SU2, okay, in dH, H being an arbitrary SU2 element, which act here on each one of them. And this I call J1, J2, J3, J4, and 1, and 2, and 3, and 4, remembering that it doesn't really depend on these 4 directions. It depends on the 4 direction up to common rotation, so it actually depends on the angles between them. So it depends on the 4 areas and all the possible angles within them. And this is a state that corresponds to a given geometry of a tetrahedron. Clear? And I have explicit formula. I can write it in terms of this, in terms of this matrix element, and so on and so forth. So now I can ask a question, which is the following. Now take a four simplex, a given four simplex. Okay, I have 1, 2, 3, 4, 5 tetrahedra. Fix the geometry of this four simplex. Choose it. Okay, and the geometry of the four simplex determines the geometry of each one of these tetrahedra and determines the area of each face. So I can write a state which has all the areas sharp and all the geometries I want by putting in the intertwiner here, 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 and here, here in each one of those states. Okay? And so I have a state that depends on the geometry of a four simplex. I'm not doing it explicitly, but this can be done on the basis of all the equations that were in the black box at some point. Now this is a state on this spin network here, so I have the amplitude associated with that. The amplitude of the spinform amplitudes of the of this object here. And this is a number. Okay? And the question is, does it have anything to do with the amplitude, the Regge amplitude, which is IA over each bar, the sum of the triangles of area of the triangle theta, where the area of the triangles are the area of the triangles of this geometry I started from. And the theorem that Barrett and his group proved says yes, this is in the limit in which this is large. So if the J is large enough, there is a direct relation between this. Essentially, this is this plus its complex conjugate. I'm going to do it a little bit more precisely tomorrow. But the large J limit of this gives exactly this thing here. Which means that this funny amplitude, which seemed to be just defined in terms of combinatorics of groups and didn't seem to have anything to do with geometry of Einstein equations, in the large J limit, in the large quantum number limit, so in Bohr classical limit, gives, at least locally, for one tetrahedron, the Regge action, which is the one that in a suitable limit in which you refine the triangulation, give generativity. I've given you the sketch of what is the core of the Barrett theorem and how to think about it. You have to use this coherent state. So tomorrow I'll be a little bit more precise about this coherent state, and I'll give you more detail about this theorem. Now is 45, so I'll stop here.
So, I have a question.
Yeah.
So I see an obstacle to doing this, which does not have to do with coherent states.
Yes.
Which is the fact that in the Regge calculus, when you compute a curvature, you have to hinge around maybe a bone or whatever dimension you are in, and that, in terms of the dual graph, is non-local because this could be an arbitrary long cycle that you need in order to compute the curvature. Whereas you say that A is local.
Yeah. So, good. So, what you're saying is that the curvature here is 2 pi minus, but the 2 pi is conventional, the sum of this and this and this and this angle. So you need all this all the values around. In fact, no doubt that the curvature here, you have to know all these links here and all these links here. So I will call R, the curvature there, it's going to be 2 pi minus the sum over, let me say, n of theta n. Okay? Now, it's the action is going to be local in the curvature, so it's going to be a sum of these terms. Nothing forbids me to take this sum and to view locality as summing this something here and 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 here. Okay, so locality is in the wedges, if you want, not in the point. It's just I'm summing all these things. Okay, and then nothing prevents me to rearrange the sum by you do all these games all the time by summing these three together, by considering these three together and associated to this point, these three together associated to this point. And so now I'm thinking in terms of the dual okay, and to this vertex I associate this term, this term, this term. To this vertex I associate this term, this term, this term. I don't see the curvature in the single vertex, obviously now, because where is the curvature? But the action of a single vertex summed to the other action is the same as summing over the point where the curvature happens to be. So it's just a rearrangement of terms.
Maybe it refers to if you have, for example, a band like this, so it's a different topology, and you can discretize so a two-dimensional band, you have a stripe and you close it. You can discretize with triangle, and at that point the dual would make a link, but it will not be a link around a node. Is it right?
That's a question I asked earlier in some other
I'm confused.
lecture, but, no, I was asking about this question today.
Okay. No, because I remember that one, and I was wondering after you made the question.
So this answers your question.
Okay. Yes.
So it's really a rearrangement of things. It's a good question, which is something that confused us at the beginning, right? We have these flat things, and we are saying, well, we associated an action to a flat thing. Where's curvature? Well, its point is that we have a number associated to that, and when you sum all together, this knows about the deficit angles, because it's a sum of angles here. So if you want, when you sum all together, you can put the A together and you get the sum of the theta. Good. Thank you.
Can I make another question? Maybe you will talk about this tomorrow, but I don't know because I want to be here tomorrow.
Okay.
So
Oh no, nothing on Friday. Friday